go to the Adam's room. So definitely it's not working, right?
No.
That plug is loose or something, no, right?
No.
Pretty tight. The power is not coming there.
Because like at this outlet, it's not working
Yeah.
either, so maybe it's like the same strip.
Right. Oh yeah, maybe some fuse somewhere, maybe fuse the circuit breaker probably.
Maybe.
Okay, let's go.
Alright, let's go.
Adam's room.
I just got it like that.
You want some milk?
That's fine. You don't have to.
Oh.
Sure. Yeah. You guys are nice cameramen.
Again, you're lying.
Yeah. Good, Saka. You won't believe what happened. Please, nobody get hurt. It's just a broken outlet.
So the projector is not working there.
Yeah.
Message to Chandra. Oh, Chandra didn't come in?
Yeah.
Yeah. Tell him.
That's like it. Oh, this is just a one whiteboard and I forgot. So I only need one camera. Thank you.
We're back.
You have meeting?
No, I met her on the way.
Oh.
See from you.
Yeah.
We will start next week.
This here?
Yeah. So I put it through this
But,
way.
I won't take for statistical today. I'm going to go
It's a
home and
micro.
complete that thing.
So I feed it to this
Because
one.
I can't tell him anything. I started doing that, so I'm going to finish it up. What happened in the other?
The power
Power
strips.
was not working.
Yeah.
Oh,
Then the battery was
Here, I'll show you. Plug it into this port, the very left.
Good.
All right, thank you.
No, you also have power, right?
Yeah. Crisis averted. Oh, well, let's see about power.
We posted the new homework, so. So, I need like 2 minutes to finish this chapter. So, the electronic properties. So far we are talking about phones, right? So if you remember, this is the last thing we talk about, right? For any metal, high temperature and low temperature. So if you remember, for high temperature, usually they go like 1 over T dependence, right? So this is the, remember the thermal conductivity. So this, if you remember K, now I can use these things. Thermal conductivity is usually given by 1/3 of the heat capacity times your velocity times mean free path, right? So we know how each one of them temperature depends. So this one we already knew, right? That T cube and VR, and so others we talk about gamma depending on the temperature, right? So how they are changing. So from that we showed for low temperatures they go like T cube, high temperature they go like 1 over T. So this is very important. These are especially true for metals, but even semiconductors they have similar behavior. So then we talk about remember the phonon scattering. So if you have two phonons, they can actually collide and make the third phonon, right? So in that case you can have energy conservation is always there, right? So the photon conservation you can have with the third phonon, but sometimes if your energy is much higher, so then you need another contribution from the G vector, right? So that's the important thing. So it depends on the the energy or the temperature. So everybody remember in two-dimensional space, this is the reciprocal space. So this basically remember these are G vectors, right? In the reciprocal, this for simple cubics that is 2 pi over 8, right? So separation between two. So now if you make the Wigner-side cell, this is called the Brillouin zone, right? The Wigner-side unit cell is basically the Brillouin zone. Now if you have two phonons, suppose this has phonon wave vector q1, so that means your momentum is h cross q1, right? I hope somebody will come there and check if somebody is waiting there.
First week.
Next week, yeah.
Not yet.
I'm waiting for that.
Yeah, we are waiting for that score. But actually, I think he's not depends on the blackboard points for the
I know that, but we can see that was correct or not.
Yeah. Actually,
From Finland, computer science.
that's why he's not giving the
Yeah.
Okay, so now if you have second phonon, if that has wave vector q2, so this one has momentum of h cross q2, right? So the energy also we know this one has energy omega 1 h cross omega 2. So now if you by combining these two phonon, if you get the third phonon, we know q1 plus q2 should be q3, right? So if you do this one, so you know how to add two vectors, right? So then q1 plus q3 will be something, if you make this one, so that q3 should be something like that, right? This one plus this one, q3. That one has wave vector of h cross q3. In this case, these two will be equal because that is within the first Brillouin zone. So if we have this kind of process, we call this a normal scattering event. We call it N process. Because your resulting wave vector is also smaller, so that it is within the first Brillouin zone. So in this case, you can easily write h1 q1, this one equals h cross q3, right? What is the direction of q3? So this is, if you component in the forward direction, right? Q2 also forward direction, Q3 also forward direction. That means there is no much impedance for that heat transport, right? So if you have the normal scattering, so heat can easily transport without getting too much impedance from other phonons or anything. So this is what in this case, no resistance to heat flow. That's why we call this is a normal process. But just imagine, so this is usually true where, like I said, low energies or low temperatures. Typically, remember we talk about everything in terms of the Debye temperature, right? If you remember, Debye temperature is given by that H cross omega d over Kp, right? So this omega d was that cutoff frequency. So when for smaller temperatures, this is the usual process taking place in metals. So, but if you these wave vectors are much larger. Suppose I have Q1, same thing. I have Q1 like this, then Q2 also large this. Now, if you add these two, what will happen? Your resulting wave vector will be out of the brilliant zone, right? So if you join these two, you can see Q3 will be here. So if we have Q3, then to have the momentum conservation, we need to flip it by G vector to make your Q3. So that's what happened here. So this is Q1 plus Q2, right? You know how to add two vectors, right? Q1. So then, so this is still outside the first brilliant zone. Then how do you bring it back? You have to add or subtract G vector, right? G means this 2 pi over A vector. So you have to subtract this length in x direction, right? If you do that one, what do you get? So this one minus G, that means this is your final vector. So that means ideally this one, this Q2 plus H cross G, right? So you need to have G vector to insertion. So this is called the Umklapp. That means it's actually flipping. So it's a German word, I think. Flipping over. So when this happens now, actually, yeah, you can write the equation. So that's the G vector. So then that is what we talk about, right? So now if you think about Q1, Q2 have the forward momentum direction. How about Q3? Q3 has opposite direction, right? Because here Q1, if you take this component this way, Q2 also this way, Q3 what is this component? In the opposite direction. That means this has some resistance to the heat flow has a resistance, right? So that's what we say, two phonon combine to give a net phonon with opposite momentum. So this means that is a resistance for the heat flow. So this is called the U process, N process and U process. This is important when you talk about phonon heat transport. Okay, I think that's all I want. So this usually happens much higher temperatures compared to the Debye temperature.
So in N process, is it gain? And
Not gain, so there's no loss.
no loss.
Yeah.
Okay.
Because okay, so let me now. So that's the end of that phonon lecture. So no, okay, this is next one. Download it from the code. Let's see.
You guys have their emails? I messaged Chandra.
What's that?
I
Oh
messaged
yeah,
Chandra.
just make sure. Yes.
Yeah, the other two.
No, the girl.
Okay. There's one other. I thought we had contact.
So they will anyway look around here right before they. I'll start from. One second. Okay. So this is a completely new chapter. Okay, so today we are going to talk about electronic properties. So first we start with metals, then we'll go to the semiconductors, and maybe a little bit about dielectrics. So today I'm going to give a very brief introduction about something called the free electron gas. So metals, so we assume as electrons, so they are free, so they are not tightly bound to the ions. So when the electron comes out, so we call that as a free electron gas model. Very crude model, but it can explain a lot of interesting properties. So then also, since you have these free electrons, if you have electric field, they respond to the electric field by making oscillations. We call the plasmons, right? That's very important, like surface plasmons, volume plasmons. Now we have the surface enhanced these plasmon things. And then remember, we already talked about heat capacity from phonons, right? So now we'll see heat capacity coming from the electrons. So then electrical, we talk about thermal conductivity, right, or thermal resistivity. Now we are going to talk about electrical resistivity. Everything is now electron charge related. So later we'll talk about something related to electronic spin. So that's where the magnetism is coming, right? So then the whole effect. So thermal conductivity from the this electronic gas. So then some limitations of this free electron gas. So what is the free electron gas? This is the most I think simplistic, right, model you can really make use of. So if you have, what is the metal you have? All the atoms, right? So atoms in crystalline form, let's say. So each atom has nucleus with neutrons and protons. So then we have electrons, right? We have co-electrons and we have the valence electrons, right? So typically these valence electrons, they are loosely bound to the atom. So in metals, these ones actually not exactly belong to the given atom. So it can be maybe shared with another atom, or it can be even free to move all around in the metal. So even electron coming from the other next atom, that one can also just doesn't belong to one particular atom. So that means all these electrons, so coming from each atom, so they make some kind of electron gas, right? So that means they are moving around. So that's why they can easily carry heat or carry electricity and things like that. So when you use this free electron model, we really, so when this electron comes out, what happens to this atom? That becomes positive charge, right? So that means this is ion. So that's a positively charged ion, but they are immobile. So they are fixed, right? But these electrons with electronic charge, they will move around. So ideally you have to consider interaction of these electron with ions, right? Also electron, they can also interact. So that's really difficult problem, electron interaction to address. But electron for ion interaction is easy to address. So the free electron gas means we really even neglect that ion electron interaction. So that means actually if you really consider, so take particular ion here, right? So what is the, if this charge Q, what is the potential for this one? We know it is going like 1 over, right? So something like, if you take from center, so it's going like this, so then it's going to infinity, like 1 over R. So here also going like 1 over R. So if you have a next one, that one also, if you take from the center, we know it is going like this, 1 over R. This side also is going like 1 over R, right? So for each atom you can draw the potential, 1 over potential term, like this, right, this dashed line. So now if you collect, add all the these terms, what do you get? So you can make something like, when you add, it becomes like this, right? So that means total potential, you can consider as what is the best approximation you can get. You can actually make something like this, like sine, right? So that's something you can approximate. But in this free electron model, we completely neglect this potential. So that's pretty simple, right? So that means if you take, this is the edge of your sample, so that means there's no potential. But here, in this case, you need to have, suppose this one has some reference energy. But in this case, ideally this you can consider as some kind of, this kind of potential, right? But here we completely consider this potential to be 0. So that's very crude, right? But that makes everything so easy. Why? Now you can solve the Schrodinger equation, right? If you consider your 2m, if I write like single one-dimensional case plus this v psi v times psi, this v is 0, right? So then this become really easy equation to solve. So that's why I think they pick that way. So later we will show, we can introduce some potential to overcome some of the limitations in this free electron gas. So then what is our picture? Our picture is going to be simply, this is the picture. You can see your potential is completely 0. That means no ion electron interaction. So this is some potential with respect to your reference. Is that clear? So I take your potential as 0. So here outside, this is the metal you are talking about. Inside the metal, your potential is completely 0. This is the free electron gas model. So everybody knows how to solve this one, right? So if you use this one, so what we get here, typically d squared psi over dx squared equals negative 2m e over h bar squared times psi, right? So usually we write this one as k squared familiar with this one, right? You know, to write the solutions, you can write as a, say, sine kx, cosine kx, you can write sine as x as a sine kx plus b cosine kx. So then if you use, yeah, but before we go any further, so how do you justify this such a simple approximation, right? Actually, it's not too bad if you consider what is happening here, because we know metals, they have very high conductivity. That means they have large number of electrons, right? So that means these electrons, we know they are loosely bound to the atom. So that's one thing. Next thing is, so if you take the atom, so this is positively charged, you have all these protons, right? You can forget about the neutron, they are neutral, right? But if you take, mostly we are talking about the interaction of the, please remember, in metals we are only talking about the valence electron. So that's the one participating in the conduction mechanism. That's the one becomes part of that electron gas, right? So if you take this valence electron with iron, it's going to be kind of screened by the other electrons, right? So because if you look at the interaction, we know these two interact each other, right? But there are intermediate electrons here. Then there's some kind of screening. This screening is an important effect. Screening effect by the other electrons. So that's another way. So that is also kind of can justify why we this the approximation is valid, right? So next thing is, we know at this point, closer to the ion that has the lowest potential energy, right? Potential energy decreasing. Lowest potential energy means highest kinetic energy. That means the electrons spend very little time closer to the ion, because higher kinetic energy, that's pass through very quickly, right? That means that spends very little time near the ion. So that means you can also make that argument strong, right? So if it spends more time here, then you cannot neglect that interaction. But if it stays very shorter time, so that means the interaction can be kind of neglected. So yeah, if you do that one, actually, then also in this model, how does the conduction happen? So this is also another very important thing, like, so if you have these ions here, right? So these electrons, we are talking about the electron. So these electrons, if I apply electric field, what happens? If you have charge, if I apply electric field, it will experience a force, right? Force is given by E times E. That is the force. If you have a force, what happens? Newton's second law says it should accelerate. That means it should have acceleration. That means if I have electron, if I apply electric field, that it should indefinitely accelerate. That means it's the velocity should keep increasing. So if that happens, so once you apply electric field, this will gain maximum infinite velocity, right, or energy. So but that doesn't happen. Why? So when it receives this energy, it will move, but it collides with the ion. So then we made this very strong assumption. We call this the relaxation time approximation. So when this electron, suppose because of the acceleration, velocity increases, right? When it receives this velocity, at that point when it collides with this one, this is very important, that velocity immediately goes to 0 during a time called relaxation time. See, this is gaining velocity, but at some point with that velocity it collides with iron, then that velocity goes to 0. Suppose initially you have momentum mv, so next momentum will be 0. Then again it starts with 0 velocity and accelerates until it collides with the next ion. So that's what happens. So if I have this electron, it's accelerating, then at some point it's getting collided, then goes to 0, then again it's starting. But overall, that moves in the direction, actually in the opposite direction of electric field. Everybody remember, the charge has negative E, right? That means if I apply electric field, electron should move to the opposite direction, right? Overall it moves in the opposite direction with some velocity, average velocity V. So we'll do this one little later. Okay, so then also if you take free electron model, so if you take, for example, sodium atom. So sodium, if you look at the electronic configuration, we have two electrons in the 1s2, 2 electrons in the 2s2, 6 electrons in the 2p6, 2 electrons in 2p, then 6 electrons, right, in 2p orbital, then only 1 electron in the 3s orbital. So this is the valence electron, right? So these are co-electrons. So typically, everybody remember, right, this one typical. Now the valence electron, what is the principal quantum number? N equals 3, right? So then we have L is 0, right? L, remember L equals 0 is s orbital, L equals 1 is T, L equals 2, D like that, right? So this basically, this one has N equals 3, L equals 0, right, that electron. So now also if you look at this one, this is really interesting. If you take the sodium metal, we know they are in BCC structure. So if you look at in the crystal, so typically if we assume like this, right, then the electron should have some this ionic radius, right? So but if you, in the sodium, if you measure from center to center distance, so typical ionic radius is, the nearest neighbor is 3.7. So that means if you take this one to this one, 3.7 angstrom, but these electrons coming from this one and this one, so the wave function of that electron, they are really overlap. That means this atom also you can think about is not like this, it is kind of overlap that one. This electron coming from this one and electron coming from this, they are kind of overlapping that region. So now if you look at the radius of the this the 3s electron, so if you measure that one, actually that has 1.9. So 1.9 means if you take that is the radius of the third shell. So if you take the double of that one, that is 3.8. This should be 3.8, right? Because this is 1.9. This is 1. You should expect 3.8, but if you measure that distance is only 3.7. That means it's kind of overlap, right? So that's actually also explains that electron is not really belonging to one particular atom. So it can be shared with others. So that means if you take the other one also like that, that means this electron, you cannot tell it just belonging to this particular electron. So that's actually belong to all the atoms. That's why we call this a free electron. Okay, so now if you consider this model, we can easily do this Schrodinger equation, right? So if you solve this one, so if you apply the boundary conditions, we know wave function. Actually, how do you solve this one is pretty straightforward, right? So if you take this, if you write this one, d squared psi over dx squared is minus 2m e over h bar squared, right? Psi, then we call this one k squared is 2m e over h bar squared. This is important. That means E is given by h bar squared, k squared over 2m. So the solution for this one you can write as a sin kx plus b cosine kx. So if you look at your wave function here and here, they are going to be 0, right? So if you take wave function at x equals 0, this is 0 means sin kx 0, this 0 means your b is 0, right? So that means this becomes 0. So then if you take the x equals L, so then I can write this one as psi, then A sin KL also becomes 0, right, at L. So this means, this is 0 means sin, what is sin? Usually 0 is n times pi, right? Any 0, pi, 2 pi, all these are 0. That means you can write your K as n pi over L. So I can call this one K related to this n. So now I can write the energy here, E for nth state, I can write as h bar squared, Kn means now pi squared over L squared, then you have 2m times n squared. So this one, we know this has discrete energy states, right? How does it go? So if you start from E equals 0, then we have E equals 1, energy is n equals 1, right? H bar squared, pi squared over 2m squared. Next one will be 4, right? 2 squared. This goes like square, that means your spacing becomes more and more. So then also we can calculate lambda. So k is, if you know k from here, so k is usually given by 2 pi over lambda, right? So that means if you take your pi and pi, you can write your lambda is actually 2L over n. So that means n equals 1 means this E1, your lambda is 2 times L. So that means it is something like this, right? Next one, n equals 2 means lambda equals L. That means, so you can calculate the energies using this equation. So I have, so you guys know these things here. So here everything, these are in terms of h bar squared over 2m pi over L squared, then everything is in n squared, right? 1, 2, 3, you can see how the spacing increases. N squared, right? Later you will find if you have the Bohr atom, if you have Bohr atom with 1 proton and 1 electron, in that case you will find your energy goes like n squared. That means this energy spacing is getting smaller and smaller, right? So 1 over n squared. But here it goes like directly n squared. Okay, so now let's talk about the density of states. So then we are going to discuss something called Fermi energy. Probably this is one of the most useful quantities in metals as well as semiconductors. So if you do this one, so again when u equals 0, we use this one, then the same thing, right? Z squared, k squared. Then the wave function, if you write this way, so the sine one I can write as this way, right? So EI, so that's basically a traveling wave is, we already talked about this one. So what is that? E equals h bar squared, k squared over 2m. That basically is a parabola, right? In k vector, your E becomes, that's your, this is the actually dispersion relationship. Right? Remember in the phonons, how was the dispersion relationship? Phonons, actually E was, in phonons that is E was H cross omega, right? So, but then omega with K, we know how it is, right? In the elastic medium, that is straight line, slope is Vg, right? If it is a monoatomic one, it is something like this, right? Sine kx over, so k by 2. So if you have a optical mode, it's something like that. These are phonon dispersion relationship. For the electrons, they have just one, except anybody knows the dispersion relationship for graphene? Graphene is different because graphene is actually it's a zero mass. We call the Dirac fermion.
You guys like the rock?
Yeah, they have. So that means your is curvature at this point is 0. So in that case, there's no mass. You cannot use the Schrodinger equation to explain graphene. You have to use the Dirac equation. In that case, your this one goes some directly proportional to your k times v. It is more like a linear relationship, except then later I will talk about that one. But it doesn't follow this relationship.
It's more like relativistic.
Yes, it's all relativistic. Yes, yeah. Because zero mass means you have to use the relativistic Dirac equation. But in this class, we'll mostly talk about this parabolic dispersion relationship.
You said that we would talk about graphene?
Yeah, a little bit, yes. Yeah. Maybe homework at least I will give you.
Oh, good.
Yeah. So then in the this traveling wave equation in spatial term you can write this way, right? A dot r. Okay, so now I want to develop the same formalism we did for phonons to calculate the density of states. So how did we calculate density of states? So if you have, say, n, in that case we define n omega, right? So this is basically number of states per unit energy range, right? So in this case we define n e. That means basically number of states per unit energy range, right? So, but like I said, it's very difficult to calculate NE directly. So what did we do in the phonon case? We calculated NK, right? So if you know NK, that means your number of states given by either NE times NE, or you can write NK times DK. So that this one depends on the dimension, right? So if you calculate NK, you know how to calculate NE. The same thing we are doing here. So NE is basically the NK, then if you, this DE, or this DK one. So once you know NK, if you know the dispersion relationship, you can calculate your NE. So that's the same thing we are going to do, but first we need to create the k-space. In phonon, how did we do the k-space? We just took the linear chain, then we just bend it so that first and the nth one coincide, right? Then we use the boundary condition. But in this case, you don't have to do this one. If you take the sample, suppose sample as length L, if you have some kind of wave function becomes 0 at the two edges, right? So that will give you the boundary conditions. That's pretty straightforward. So if you take, let's take sample with length L in one dimension. this is L. Suppose your solution for this sample is AE I kx minus omega t, doesn't matter, right? So if you take only the spatial part, I can write as psi x is simply I kx. So now if I take, this is suppose x equals 0, this is x equals L. So at x equals 0, what do you get? So the wave function will be 0, right? So that means this part becomes 0. So psi x 0 means this becomes 1, right? Yeah. So that means psi 0 is 1 is equal to psi at L. So psi L is what? Psi as yeah, this is A times, right? Yeah, don't worry about that one. Then you get E I k times L. So that means I can write E I k L equals 1, right? So what is, how do you get 1? E I times 2 pi, the even pi times n, right? That's how you get. So that means you can write from here KL equals 2 pi n. That means your k is given as 2 pi n over L. Same thing, right? 2 pi over n. So that means I can have kx as 2 pi n x over L. So here, so it's exactly same way we got for the phonemes, right? So that means now I have my k space, right? Now I have solutions for each each n I can have kn, right? So that means I can define all the points. So the separation between each point in the one-dimensional case, 2 pi over n, because it's inverse, right? So if you take 2 dimension, you have this dimension also 2 pi over Lx, Ly. In this direction you have 2 pi over Lc, right? So that means this is your k space. So from here you can calculate just like we did before. So this, what is the volume of this? If you consider, if you take this one, okay. What is the volume of this one? 2 pi over L cube, right? 2 pi over L cube. So this actually corresponds to 1 mode, right? Because it corresponds to 1 mode. That means you can find what is the number of modes per unit volume of this one, right? So that means we call number of modes per unit volume of k space. K space volume is given by, so inverse of that one, right? That is L cube means V divided by 8 pi. We did this one before, right? So this is the number of modes per k volume, for unit k volume. Now if you have, yeah, I think here, this 2 pi over L cube, that's the volume, right? Yeah. So then you can, number of, yeah, this is 0, 8 pi cube. Is that clear for you? So then, just as in the case of phonemes. Okay, this is the now important thing. Now we are going to talk about just isotropic. This very, every direction they have same, like the relationship for k, kx, ky, kc. So then we can define, in 3 dimension it is mostly sphere, right? So then how do you calculate the total number of, here, number of modes per volume. So if you take isotropic volume, right? So this, remember this is sphere in 3 dimension, right? So if it is 2 dimension, it's simply a circle, right? two dimension, basically we are talking about is a circle with some k, pi k squared, right? Here, if this is say k, what is the volume would be 4/3 pi k cube, right? So that means if this is the number of moles per unit k volume, then you have to multiply by that 4/3 pi k cube to get the total number of moles. So now this is the important thing. This each mole corresponds to some electron, right? So moles means these are the solutions for that equation. So they occupy one electron. So that means if you take this sphere, so total number of moles correspond to total number of electrons that can occupy this k space here. So when we do this one in metals, we have this very special k value we call the maximum k value that define this sphere surface. So within that surface, all the states are occupied by the electrons. So all these k points are now have electrons. So nothing beyond that one is filled with electrons. So here we are talking about allowed states, right? So you can have, if I draw it in energy scale, so that is the k space, right? If I draw in energy space, you can have this allowed state. That's what we call the density of states, right? So how many electrons can occupy this given state? These are fermions, right? Ideally you can have one, but because of the spin difference, you can have 2 electrons. You cannot have more than 2 electrons, right? For a given state, you can only occupy by 2 electrons. But these electrons can only occupy some energy. So that is more like what is the maximum, this k value, I call this kf. That's in the k space, this sphere determines what is the maximum, this k vector, that within that k vector all the states are filled. In the energy scale, so we define that we call EF, that relates to kf. So we call this a Fermi wave vector and the Fermi energy. So we know how these are related, right? How they are related? EF squared is always, this relationship is true. If I know kf, I can find EF. So EF means in the energy diagram, what is the maximum energy? Up to that point, all the states are filled with electrons. All the other states are unoccupied. These are called the occupied states. Occupied states. These are called the unoccupied. But these are all available for electrons to be filled. But not all electrons are filled up to the maximum. This is the, you have more states, right? But only the electrons up to this maximum energy are filled. So in the k space, all the states, because this each mode corresponds to 1 electron, right? So only up to this kf radius will occupy the states here. So all these are unoccupied, right? So everything here inside occupied, here, outside is all unoccupied. Is that clear? The two things you have to understand now. So now you can easily calculate what is the, we know this is the number of states per K space, right? So then if you consider this one, how many total modes will be there? That one times 4/3 pi K. Right? So that means I can say this is, actually next one, I have this one. Yeah, you can understand what I was trying to say. So what is this orange part? Those are the states filled. So the states outside are unfilled. So that defines the Fermi. So we call this surface as a Fermi surface. So what is this surface? It's really the spherical shell, right? That Fermi surface is the sphere surface. Is it clear for everyone? Yeah.
So no other electrons can occupy those states outside of that shell?
No, so because that defines that one. So only if you provide more electrons, that means this cave will be larger. Yeah. So that means it can occupy more electrons. Right now, for a given cave, so it can only occupy that many electrons. So then you can easily calculate that number of states as this is the total number of the per K space, right? So then you multiply by the volume of the Fermi surface. So that what will this one give? Actually n by 2, because this times 2 you can have, because each state can be filled with 2 electrons. That's why I put NO2 here. So this taking care of spin up and down states. So now you can easily solve this one for Kf. What you get here? N over 2 equals V over 8 pi cube times 4 by 3 pi Kf cube, right? So you can see 4 times 2, 2 and 2 cancel. Then I get N over V equals N over V equals pi Kf cube over this one becomes over 3 pi squared, right? Yeah. So if you do this one, so you get 3 pi squared. So yeah, if you write K F cube V is basically 3 pi squared. Usually we write this NOV as simple n. N is the electron density, that means number of electrons per unit volume. That means 3 pi squared n, 3 pi squared n, or this pi also cancelled here. No, there's no pi here. 3 pi squared n, yeah, that's it, right? Yeah, then it means Kf equals 1/3 of this. This is an important expression. This is true for three-dimensional case. I will give example problem for you to work on the three-dimensional case. So then what is the, once you know this one, you can calculate the Fermi energy. Fermi energy is basically, just use this equation, Kf, you just put this one, you get this. You can see when the n increases, what happens to Ef? Increases, right? Because that means you are putting more electron, that means your Fermi sphere is getting bigger, right? That's why typically people do something called the doping. If you dope, what happens? Your Fermi energies move into higher energy and Fermi sphere becomes larger.
This is all because of Pauli exclusion, just because you can only have two.
Yes, yes.
So there's nothing like this for bosons.
Bosons, there's no limit, yeah? You can have any number of, yeah. That's why both signs and condensation happens, right? At the ground state, all the electrons are occupying that one. But that cannot happen for fermions, yeah. So then let's do, actually I want you to just follow this formalism how to calculate the, so still we didn't calculate the density of states, right? So density of states, let's do this way actually. Like I said, here I will call G instead of N. So GK dk, that's dn, right? Number of states given by either gk dk sorry, dn whatever time equals ge de, right? So let's do for three-dimensional case. Three-dimensional case, you can easily write gk dk as so if you take what are the total number of states, if you take in the three-dimensional case, please look at this one. This is, I think if you do this way, you will never make a mistake. So this is my k space, or the k points here. If I take a sphere with radius, say k, and if I take, this is say some shell, a second shell with the difference of your k as dk. You get k, then you take the next shell, k plus dk. Right? In this one you have this k points here, right? So then I can write how many states are here in this annular region. How, that's gk dk, right? So what is that one? So what is the total volume here? Actually in this case, yeah, total volume will be this surface area times dk, right? What is that surface area? 4 pi k squared times dk. So then to find, we know each one, you have to divide by 2 pi over L to the power 3 in the three-dimensional case. So if you do this one, you can say dk, then you get gk as what? Gk is 4 pi k squared, then this is v divided by 8 pi cube, right? That's how we calculated this 2 pi squared, right? K squared VO 2 pi squared. That is what this one is. V k squared or 2 pi squared is your gk. Let's do this one for two-dimensional case. Then you will understand this. Let's do this one for two-dimensional case. Then what do you do? In the two-dimensional case, I don't make a sphere, right? What do I make? Not circle, is just a perimeter like this. So then, this is radius k, then I make another one, so that one has a dk width. So then if you look at number of states here, so I can find dn, that is dk, gk, dk, right? What is that one? 2 pi k times dk. That's the total area, right? 2 pi k times dk, that is, this pyramid is 2 pi k times dk is this area. Divide by 2 pi over L what? Square, right? So it's exactly here. Here I had 2 pi over L 3. Here I had 4 pi k squared dk. There I have 2 pi k dk. So if you do that one, what do I get here? 2 pi. So that means gk, this dk cancel, right? Your gk is 2 pi k, the L squared, that becomes area, right? Divided by 4 pi squared, that means you get 2 pi here, right? Ka divided by 2 pi, that is gk. Gk goes like k. Here gk goes like k squared. You can do same thing for one dimension, right? How do you do one dimensional case? One dimensional case, your dn is gk dk is equals, in that case we have just simply dk, right? So dk divided by what? what do I have here? Just 2 pi over L, right? That means your GK is simply L divided by 2. That means k to the power 0, right? K to the power 2, k to the power 1, k to the power 0. You can make the relationship. Okay, so this is all about how to calculate GK. Now what we need is what? GE, right? So how do you get GE? Let's do it for the three-dimensional case. This is always true. GE times DE is GK times DK, right? That is your DN. So that means GE is GK divided by DE by DK, right? So now GK we know K squared V over 2 pi squared. Then dE over dk you get from your dispersion, right? dE over dk, E is E equal h bar squared k squared over 2m. Then what is dE over dk? H bar k over m, right? 2k and 2 cancel. H bar squared k. Yeah?
Sir, cannot you simplify?
Yeah. So now if you divide by this one, what happens? You have m divided by h bar squared k. If you do this one, you can calculate this one as this 1k cancel. You get mv over 2 pi squared h bar squared k. K is basically square root of 2me divided by h bar squared. Is that agree?
Yes.
So h bar squared is actually, this becomes h, right? So then this becomes q. So actually you have to include another 2 here because we didn't consider the spin one. Ideally you have to have another 2 here. That means your expression will be, I can take v divided by 2 pi squared h cube. Then I have this m here half, that means m 3 by 2, right? So then 2 also, 2 here 1 2, that means 2m 3 by 2 times square root of e. This is the important thing. So you can see your density of states. So here everything is, you can see how we did this one. So if you do that one, this is the final answer you get, right? V over 2 pi squared h cube 2m 3 by 2, yeah, square root of e. I think you can follow this one. Same thing you can do here, right? I don't have to do it here. So just actually, if you do this one, you will find your G is independent of E. Because K and K cancel. So in 2 dimension, has anybody noticed that? I will give some homework problem to work on that.
So suppose like in linear case, we get a,
What's that?
like if you go to the linear case, then
Yeah, then it goes 1 over E. Yeah, so that's actually, you can show in the 3-dimensional case, your density of state GE goes something like square root of E. So that means if you draw this one, density of state versus E, this is going something like square root of E, right? But if you calculate for 2-dimensional case, actually this is constant. Can you show that? This is GK, right? GE, how do we calculate GE? DE is GK DK, so that means GE is GK divided by DE over DK, right? So GK is KA over 2 pi, DE over DK is that h bar squared m over h bar squared k you can see this K and K cancel. So what you get is MA over 2 pi h bar square. So that means for two-dimensional case, your density of state is actually constant. So I would encourage you to do for one-dimensional case. If you do that one, you will find this is two-dimensional, 2D GE is a constant. So 1D GE goes like 1 over square root of. So that is basically yeah. So 3-dimension, 2-dimension. The 1-dimension is basically 1 over square root of e, something going like that. Right? So anybody know 0 dimensions? There is something called 0 dimensions. You know any good thing? Like quantum dots. So, typically the way you define the dimensionality is how many good quantum numbers are there. In 3 dimension, so all kx, ky, c are all good quantum numbers, right? If you take 2 dimension, there are only 2 good quantum numbers. Other direction, that is quantized in the third direction. That's why it's, so that means you have only 2 the well-defined quantum numbers. So in 1 dimension, actually 2 directions are quantized, only 1 free motion. In 0 dimension, all 3 dimensions, they are confined. So that's what we call the quantum dots. If you calculate for 0 dimensions, actually your density of state becomes, later we'll do this one, is some delta function. That means they are more like, so right now we are talking about 3-dimensional case, right? We'll do some homework problems to go through these things. So everybody familiar with this one now? Please don't remember the 2. These are electrons, right? You need to have 2 states for 2 electrons can be in these states, right? Okay, so now remember we calculated Fermi energy from that multiplying by that your number of modes, then we multiplied by kf cube, right? That's how we got the number of electrons. But you can do that one from the density of state directly. How do you do that? So I know that density of state, right? So density of state has some constant times square root of E, right? So now if I density of state is, what is the definition of density of state? dN is actually GE times dE, right? Right, if you take integral of GE over dE, if I integrate from 0 to Fermi energy, what do you get? That's the total number of electrons, right? So this is the density of state, that is dN, right? GE times dE. If I integrate this one, the limits are from 0 to EF, right? Because only up to EF they are filled. So then what do you get here? Total number of electrons. So now I know GE expression, that is this one. Oh, here N is this clear for everyone? So now we just put that expression, do this one, go ahead and do the integral, we know E, this becomes E 3 by 2. If you do this integral, you get that exact expression. The EF is, remember this is 3 pi squared N, right? So that's another way to do that. Starting from the Fermi energy. So this N over V means simple name. So we call this one the Fermi surface, this is the Fermi wave vector, so this is the Fermi energy. So basic, idea of Fermi energy means the Fermi surface means surface of the Fermi sphere represent the boundary between what? Occupied versus unoccupied states of the, but this is another thing to remember. This formalism is all for zero temperature, 0 Kelvin. So later I will see how the finite temperature play role in this one. So this is what volume exclusion principle, right? We talk about. Yeah, you can have both spin up and down. So once we have this Fermi, this is the two things we talk about, right? Kf and Ef. So if you take any regular metals, typically this wave vector is like 1 over ampere, right? So wave vector means 1 over dimension, right? So that is usually about 1 angstrom inverse. If you take the Fermi energy, these are typically 5, 6 electron volts. These are large so then we can define some other quantities like Fermi momentum. If you know H cross, so you can consider like a momentum in this de Broglie regime, right? So you can define, if I know Kf, I can get Pf, right? H cross Kf. Or somebody can define the Fermi velocity. This is very important. Fermi velocity defined as Pf divided by m, right? Mv. If you do this one. Actually, if you take graphene, this value is much higher. That's why graphene is considered one of the very high mobility materials for electrons. Typical metals have Fermi velocity like mega meters per second. Then Fermi temperature, also if you know EF, typically we define TF as E is KT, right? So these are some of like typical like 10,000 Kelvin. Is that almost right? Oh yeah. I'll stop from here. So next class we'll talk about actually the finite temperature affecting.
Okay, so like all that was just for.
This is all for 0 Kelvin here.
Okay.
Yeah. So then the only thing